Alright, for our thermal transfer questions, this one is looking at a glass window that is actually just going to able to transfer some of that energy through. So we can apply our equation straight to this one. So we get that our rate of thermal energy, so delta Q on delta T, is going to be equal to the thermal conductivity constant times by the surface area times by the difference in temperature divided by the separation between. That could be L or it could be a D for the depth of it. This one, we're asking for the rate of thermal transfer. So delta Q on delta T is a measure of joules per second. So that is our measure of watts. And that, seeing that we're talking about thermal energy in this situation, we are going to have the rate of thermal transfer in this situation. So therefore, we can just start plugging in some numbers. We've got our thermal conductivity constant, which is 0.5, times by our area, which is 1.2 meters, times by our difference in temperature. One is +5 and the other one is 20 degrees. So our difference in temperature is 15 degrees, divided by the separation between, which is 5 millimeters. So we need to convert that to meters. So that will be 0.005. which should come out as being 1,800. The answer up there is in kilowatts, so we divide through by 1,000, so we get the 1.8 kilowatts. Our next question, a layer of ice of uniform thickness, 7 centimeters, has formed on the surface of the lake. The temperature above the ice is -12, and the temperature of the water below the ice is at 0 degrees Celsius. So in this situation, the water is actually giving energy to the air itself. In the first question, we want to calculate the energy transfer per unit area. So for A, we're going to have our change in thermal energy over a change in time. But we're also going to see per unit area. So we're also going to divide through by A. And that is going to be equal to our formula of K delta T on L, which is then going to be equal to our 2.1 of the thermal conductivity of ice times by the difference in temperature, which is just going to be 12 because we've got 0 and -12. So therefore, we're going to have a difference of 12, and our thickness is going to be 7 centimeters, so we're going to have 0.07 in our value there, which should come out as being 360 watts. But because we've got that area over here as well, we're going to have per meter squared. For part B, we've got calculate the mass of water that freezes during 1 hour. So we need to calculate how many seconds there are going to be in an hour because watts is measured in seconds. So that means that 1 hour is equal to 60 minutes times 60 seconds. So this is going to be equal to 3,600. We want to go below 1 square meter. So that means that our rate of thermal transfer per unit area, we're going to multiply that by the area, which is going to be 1. So our rate of energy transfer is just going to be delta Q on delta T. And because our area is 1, this is just going to be equal to 360 watts. We're wanting to see how much energy is given up by the water. So that means that we're going through a latent heat of fusion. So we're going to see how much energy is going to be transferred. So that's going to be the time, the seconds that we've got there. So 3,600 times by our 360, which is going to be equal to 1296000. Now we know how much energy is going to be transferred. We know that Q is going to be equal to MLF. So our mass is then going to be equal to Q divided by LF, which is then going to be equal to 1296000. But our value up here is in kilojoules. So we're going to divide our value here by 1,000. Divide it by the 334, so it comes out as being 3.88, which is equal to 3.9 kilograms to 2 significant figures. For part C, we have the density of the ice, so density is equal to mass divided by volume. we're wanting to calculate the rate of growth of it. So we know that in 1 hour it's going to produce 3.9 kilograms in 1 hour worth of freezing. So therefore, we're after our volume, which is going to be equal to our mass divided by our density, but we're after the increase in the thickness. So therefore, we're going to break our volume into area times the length, which is then going to be equal to our mass divided by our density. We're after the depth or the growth in it, so therefore it's going to be equal to L, which is then going to be equal to our mass divided by our density times by our surface area. From that, we know that we've got 3.9 kilograms. We're going to divide that by the surface area. The surface area is 1 square meter. The density of ice is going to be 920 kilograms per meter cubed. This is going to get us a number of 4.23 times 10 to the negative 3, but that's in meters. So that would be 4.2 millimeters per hour. Last one. On a winter's day outside, we have a temperature difference. This is the idea of a double glazing of glass. So for our single pane of glass, we're just looking at a window. Our A is going to be very similar to what we did before. So our delta Q on delta T times by our area is going to be equal to our thermal constant times the difference in temperature divided by the separation between them. So this is going to be our 0.5 times by the difference in temperature, which is going to be 25, divided by the thickness of the glass, which is 4 millimeters, so 0.004, and that will give us our answer of 3,100 watts per meter squared, which we can convert to kilowatts as being 3.1 kilowatts meters to the minus 2. So per square meter, we are losing 3.1 kilowatts. Part B is a little bit of a slight annoyance, but also slightly of a tricky question. The main thing that we've got here is that we have air in between our bits of glass. We may think that we should do is one plane of glass, another pane of glass, and then we can put some air in between with the hot side over here and the cold side over here. The only problem with this is that when we're looking at the thermal conductivity of our different items, we have the thermal conductivity of the glass as being 0.5 and the thermal conductivity of the air being 0.023. So the part that's actually going to restrict the thermal transfer is the air in between. The air is going to slow down the thermal transfer. So because of that, the glass on either side is going to transfer its energy faster than the air in between. So the only thing that's affecting the rate of the thermal transfer is the air inside, because it's going to take the slowest to transfer that energy. So our delta Q on delta T per unit area is just going to be that of the air. So that's going to be delta T on the thickness of the air. So our 0.023 times by the difference of temperature, we can make the assumption that both of those panes of glass are going to reach equilibrium faster than the air inside. So we could still say the temperature difference there of 25 divided by the thickness, which is 0.01, which is then going to get us our value of 57.5, which would round to our 58 watts per meter squared.